Bien, bonjour à tous. Nous allons commencer l'exposé d'aujourd'hui et nous avons évidemment l'immense plaisir, le privilège de recevoir aujourd'hui Chris Friss. I will just say a few words to mention that Chris Friss, as you know, is Emeritus Professor of Neuropsychology from University College London, where he did a large part of his career with very eminent colleagues, including, of course, Uta Friss, but also Tim Challis, Richard Frakowiak, Ray Dolan, many of the heroes, I would say, of cognitive neuroimaging and cognitive neuroscience. Chris is also currently Niels Bohr Professor in Denmark at the University of Aarhus, and in this topic of social cognitive neuroscience that he will tell us about today. Chris is the recipient of many important prizes. He is one of these FRS, Fellows of the Royal Society, as well as the British Academy. I don't want to mention the list of prizes, but I will just mention that you received the Thyssen Foundation Prize last year, which is a very important prize, perhaps the most important prize in the field of cognitive neuroscience. This is, of course, for recognition of your important work in many different aspects of cognitive neuroscience, starting, of course, with the work on schizophrenia, for which you are extremely well known, and you published several books on the topic, and continuing on to many different domains of cognitive neuroscience, but especially looking at the interactions between multiple minds. And I think this is the major topic of your current work. If you look at Chris Friss' curriculum vitae, you will find 400 papers, which is quite amazing. You will find that I think 20 of them have been published in Nature and 15 of them in Science, which I think is unequaled even in any other domain of science. It's quite remarkable. And I will just mention your latest book, which is called Making Up the Mind. I don't remember the title in French, but maybe we could ask Mathias with the title in French. Comment le cerveau crée notre univers mental, chez Odile Jacob, traduit par Mathias Pessiglione. Et c'est un excellent livre, court, tout à fait passionnant, sur les dernières recherches dans le domaine des interactions entre cerveaux. So Chris, without further ado, thank you very much again for being here for 2 lectures.
Well, thank you very much, Stan. The secret of getting all these papers, of course, is to collaborate. I didn't actually do anything myself. And most of this talk will be about things that not only did I not do myself, but I didn't even collaborate with, which is the advantage of being emeritus. I think you can start talking about other people's work. So I want to speculate a bit about theory of mind, and in particular the mechanisms that might underlie it, because there have been a lot of recent developments which I think will change our view. So this is just to remind you that I'm interested in talking about how it is that we're able to attribute mental states to other people, what they know, think, feel, and desire, and by doing this we can predict what they're going to do. And this is sometimes called having a theory of mind, that is to say, realizing that you can predict what people are going to do on the basis of their mental states. And perhaps a better word is mentalizing, which is the process of doing this. And many years ago, Uta and I decided that we would ask the question, are there particular bits of the brain involved in theory of mind? And I'm pleased to say that at the time many people, I think including Stan, thought we were mad, that such a complicated thing could be reduced in this way. And I think this is one of the areas where there has been a surprising amount of replication. So that however you study theory of mind in the scanner, whether you read people's stories or make them read stories, whether you show them static cartoons, whether you show them animations, like the moving triangles that you will have seen in Uta's talk, the brain, and they have to think about the intentions and beliefs of these characters in the presentations, you get a very similar pattern of brain activity. Whatever the task specifically is, you typically find medial prefrontal cortex, and in particular superior temporal sulcus or temporoparietal junction. And if there are any anatomists in the audience, I have to remind you that I'm a psychologist, so I'm quite happy with these enormous blobs where I'm not quite sure where they precisely are. And we'll see some examples of that in a moment. So what I want to speculate about is, can we specify roles for these different brain areas? Are they concerned with different aspects of mentalizing? And can we start to think about what are the mechanisms that enable us to do mentalizing? And this is the classic Sally Ann task, where Sally believes that her ball is still in the basket because she doesn't know that Anne has moved it into the box. So this is an example of her behavior being determined by a false belief. And this test is really of explicit mentalizing. Children around the age of 4 can do this task. They will correctly tell you where Sally will look for her marble, that is in the basket and not where it really is. But in addition, they can tell you why she will look in the basket. They know that because she hasn't seen it being moved, she believes it has remained where it is. So they have an explicit ability to understand what's going on. But there's also now, I think, good evidence that there's implicit mentalizing, because infants, even now I think down to 7 months of age, behave in such a way as to demonstrate that they have knowledge and expectations about other people's false beliefs. The first study was done by Onishi, who I hope is somewhere in this audience, and there have been several studies since getting it down lower and lower and showing greater and greater sophistication on the part of these infants. And of course, in addition, it is now being claimed that mentalizing of a kind can be observed in corvids such as ravens and scrub jays and possibly some other animals. And I'm assuming that this is a kind of mentalizing that is implicit and maybe not the same mechanism involved in the explicit mentalizing that 4-year-old children can do. And here is some recent examples from Dana Sampson, Ian Appley, demonstrating implicit mentalizing in adults. So this is a point of view task. You see a room with this avatar in it, and there are dots on the wall. And then the traditional experiment would be, you would ask the question, how many dots can you see? So here the answer would be 2. How many dots can she see? And the answer would be 1. But the trick that Dana Sampson employed was to simply ask only the question, how many dots can you see? And what you find is that if you are slower to answer that question if there's an incongruity between what you can see and what the avatar can see. So the mere presence of the avatar slows you down to answer the question, how many dots can you see? And this is contrasted with a piece of wood which is green on one side, which doesn't produce this effect. So you seem to, because this goes against this is actually going against your performance, it suggests that this is an automatic effect, that you automatically take account of the fact that this other person has different knowledge from you. And this has been to some extent confirmed by adding a cognitive load. So you essentially do the same task again with and without a cognitive load. That is to say, you were given a series of random numbers to remember. You then do the task, you then repeat back the numbers. If you're actually using cognitive effort to notice what the other person can see, then the application of the cognitive load should reduce the interference, but in fact it has no effect whatever. There's just as much interference from what when the avatar can see something different from you, even in the presence of cognitive load. Whereas if you're asked how many dots can the avatar see, that is to say, if you have to adopt their point of view, then the cognitive load does slow you down. So I think that's evidence that this is a case where you automatically take account of someone else having different knowledge from yourself. And of course, I should have mentioned that in the Kovacs experiment on infants, where they again show that the knowledge of the false belief of another creature, not even present, can affect your performance. This applies to adults as well as to infants. Another example, I think, of this automatic, implicit mentalizing. So this particular last experiment suggests differences between implicit and explicit theory of mind. So the implicit version, we automatically track the knowledge of others when it's different from our own. Whereas, on the other hand, if we want to have explicit knowledge, we can actually tell you about the knowledge of other people. You need some kind of executive function in order to adopt the perspective of another person. So now, what about the mechanistic basis of theory of mind. So I want first to talk about implicit theory of mind, that is to say tracking knowledge and intention. And I will suggest that posterior superior temporal sulcus stroke temporoparietal junction has a particular role in this aspect of theory of mind, whereas explicit, that is to say metacognitive awareness of mental states, which you can tell people about, may depend on medial prefrontal cortex, the other main component of the mentalizing system. So what do we know about posterior STS? Well, it's been long known that it's particularly sensitive to biological motion. So when you see this character moving like this, STS will be more active than when you see the same number of dots moving exactly the same way but not actually forming a person. And there are all sorts of other types of stimuli, so moving arms, moving eyes, moving bodies, all activate this area of posterior STS, particularly on the right. Now, interestingly, this area is also activated by the Hyder and Simmel triangles, which you saw last week, even though, interestingly, the movement of these triangles is not biological in the sense that this is biological, although it is intentional. And the other odd feature, of course, of the Hyder and Simmel triangles is that you're seeing them from above, which is a very peculiar way to look at. It's not the usual way we look at living entities. And for some time, people have suggested that what is happening in this area is it's somehow involved in your ability to read intentions from movements. This is an experiment from Julie Gray's, and this is you see a video of a person lifting up a box, and the box varies in weight, and simply from looking at the video you can work out how heavy the box is. You can work out whether the box was heavier than the person in the video expected it to be, and you can work out whether the person in the video is pretending that the box is heavier than it really is. So these are all quite sophisticated inferences you can make simply by studying the movement, and all these videos activate posterior STS, and basically it's more active with the more unusual action, that is to say it's more active when the movement reflects that the box is heavier than the person thought. It's more active when the person is pretending the box is heavier than it really is. And I'm suggesting, or a number of people suggested, that rather than biological motion, what this area is involved with is in the detection of agents, i.e. things whose movements are caused by intentions, and therefore it's involved in tracking intentions. And in particular, the activity in posterior STS-TPJ reflects intention prediction errors, where you've predicted that they're going to make a certain movement because this is their intention, and they make a different movement, so you've obviously got the wrong intention. You have to update your belief about their intentions. And here are some examples. One example of this from Pelfrey's group. So you see this avatar, a target appears, and the avatar moves her eyes towards it. In other conditions, the target appears, and the avatar moves her eyes away from it. This is the activity in STS, and you see both cases the eye movements elicits activity, but the activity is greater when the eye movement is incongruent, when she looks away from the target. The assumption being that you expect her to look at the target, and when she doesn't, you're surprised. The same group have done the same thing for reaching movements instead of eye movements, and you get exactly the same result. And Rebecca Sachs has done it with people who disappear behind a bookcase, and if they come out later than you expect, you get more activity in this area of right posterior superior temporal junction, or what she calls TPJ. And this is an example of the problem of brain imaging. So this is from a very recent paper, not quite published yet, from Metcalfe's group in the States. And this is, part of this is a meta-analysis of brain regions which seem to be involved in the detection of agency. So this paper doesn't say anything about tracking other people's action, it's all about tracking your own action. So this area is more active in studies where people have to decide whether they are the agent or not of a cursor moving on the screen. And I can't remember which way around it is, the yellow areas I think are from the new study, where they deliberately put in distortions so that you find that sometimes you're not fully in control of your action, so that the movement you expect to see on the screen doesn't relate to what you just did, and again you get more activity in the same area. Likewise, in the condition where you're trying to detect, am I the agent of the movement or not, there's more activity when you're not the agent because the movements you're making are not producing the expected changes on the screen. So this is an example of prediction errors for the self when you're making movements. And what these people suggest is the experience of agency depends upon being in control. So the fewer the prediction errors, the greater the experience of agency. Now, of course, we know from people like Daniel Wolpert that prediction is a fundamental feature of motor control. So this is the standard diagram. If you have a goal of making a movement, the first problem is you have to work out what commands you should send to the muscles to produce the movement you want, the so-called inverse problem, which is mathematically difficult because there are many different ways of achieving the same goal. But you can also compute a forward model. That is to say, you can say, if I sent these commands to my muscles, what would happen, both in terms of where would my hand finish up and when, and what would it feel like? And this, you can also see whether what you're going to do, it corresponds to what you wanted to do, so you can correct things before you actually make the movement. But in particular, you can predict what's going to happen, and you can observe what's happening. And the difference between these, this is the prediction error, enables you to improve your control of movements in the future. So you want to minimize the error between the intended consequences and those predicted by the forward model. And both Daniel Wolpert and Kawato and my colleague James Kilner, have suggested that this same system for controlling our own movements can be applied to understanding the movements of others. So this is obviously much too small, but the main thing is this is a Bayesian model. So, and it probably relates to the mirror neuron system. So here is optimizing your own action. You minimize the error between the desired trajectory and that predicted by the forward model. In action perception, you minimize the error between the inferred command and that predicted by the forward model. So to put it in real words, what you're doing is you're saying, if the person I'm observing has this intention, then on the basis of my own motor system, I can predict, using the forward model, the movement he ought to make. And if he doesn't make that movement, because I'm predicting, that's his intentions, I'm predicting the movement he's going to make, and I'm seeing what movement he actually makes. And if there's a discrepancy between what I expect him to do and what he actually does, that means my inference about his intention is wrong, and I have to update it. So that's a very casual account of these quite well-formulated mathematical suggestions of how you might be able to predict people's intentions on the basis of watching what they do, how they move, and how you're actually using your own motor system to do this to some extent. So this would be a mechanism for implicit theory of mind. We track the knowledge of intentions of others by predicting what they're going to do. We predict their movements using our own motor control system, simulation in other words. And if they do something different, a prediction error, we change our assumption about the intention. Now, through its involvement in predicting actions from intentions, this area of the brain, posterior STS, is actually part of a mechanism for detecting agency. Because I'm now saying, having thought about this, I'm suggesting that maybe an agent is defined as something whose movements are determined by its intentions. So if its movements can be predicted from its intentions, then it must be an agent. So that's the sort of circular thing about how this bit of the system that relates intentions to movements also becomes an agency detector. Now, interestingly, even when the intention is indicated by an abstract choice rather than a physical movement, activity in this area still reflects intention prediction errors. So let me give you an example. This is the sort of thing where you're actually playing some sort of very simple economic game. This is from Matthew Rushworth's lab, Tim Berentz. The task, the subject sees a series of screens. He has to choose on each trial whether to open the blue door or the green door, because one of them will have a greater reward behind it. And the probability of which door will have the reward behind it varies slowly across trials, so that's a standard reward learning task. But at the same time, there is a person who's giving you advice about which door to open. And sometimes this advice is reliable and sometimes it's not reliable. And again, this changes slowly over time, but incommensurably with the reward. So you can actually look at prediction errors about where the reward will be, and you can look at prediction errors about whether the advisor is reliable or not. And the model fits quite well both kinds of system, both the social and the reward system. But the reward prediction errors, as usual, are found in ventral striatum. And the social prediction error, that is to say, when the person gives you advice which is not what you expect, is in posterior STS/TPJ. And in this case, you're not seeing a movement, you're just being told what advice is being given, which is simply a left door or right door. Another, yes, I can't remember whether I put that in. And there's another example I will give you of this later, where a prediction about what this person is going to do in terms of what choice they make rather than observing their movements also activates posterior STS when there's a prediction error. So that is my first part of explaining, giving a sort of sketch of the sort of mechanism that might be required for doing implicit theory of mind, that is to say, tracking people's intentions. So what about a mechanism for explicit theory of mind? And what I think is relevant here is this concept of closing the loop, which I will explain to you immediately. The problem with other people is that while you are making predictions about them, they are making predictions about you, which is much more difficult than what I've just been describing, where it's just me trying to predict what this person's intentions are. So it's not enough to represent what you expect your partner to do, you must also represent what she expects you to do. And this is an example, and I first talk about this in relation to competitive recursion. So this is Jean Maynard Keynes' beauty contest game, which the game is you have to choose a number between 1 and 100, and the winning choice is 2/3 of the mean choice of the group, or some other number that you arbitrarily decide on the particular task. And so to win, you have to think about what the other people in the group are going to do, and presumably what they think you're going to do. So extremely stupid people, if asked to choose a number between 0 and 100, will choose 50. Slightly more clever people will recognize that the extremely stupid people will choose 50, so they have to choose 2/3 of that to win, which will be 33. And even more clever people will realize that the clever people will choose 33, so they choose 22. And you go on like this, and if you're a super rational Nash equilibrium person who believes stupidly that everybody else is super rational, you choose something like 1 and you lose. And it turns out, because this is a game that's been played in Danish newspapers and on Swedish television, that if you want to win this game, and it's, for example, 2 recursions is about right. Yeah. Now, Coricelli and colleagues actually put people in the scanner while they played this game, and basically what they found is that the more recursion you did, which they think is the more mentalizing you do, the more activity you see in medial prefrontal cortex. Now, this is another example of a recursion game, although it's not presented in that way. This is, again, is competitive. This is the Inspector game. This is from Hampton and John O'Doherty's group at Caltech. So this is a typical economic game. You have 2 players. You have an employer and an employee. The employee can work or shirk. The employer can inspect or not inspect. Now, obviously, for the employee, they do best if they're working when they're inspected, and if they're shirking when they're not inspected. The employer, it costs money to inspect. So it costs them, they benefit, obviously, if they inspect and the person is shirking, and so on and so on, but they prefer to inspect as little as possible. So it's a sort of, I think it has two Nash equilibria, and you sort of cycle between them. And the nice thing about this study is that they developed 3 models of how you might play this game. So the simplest model is a reinforcement learning model. You simply choose the action that has been most rewarded in the recent past. And this is the Rescorla-Wagner equation. So this is the value of the action at this time. This is the reward prediction error. That is to say, you make the action, you're either rewarded or you're not rewarded. And if you're rewarded, you're obviously likely to make it again. If you're not rewarded, you're less likely to make it again. And this is the learning rate for how far back in time, effectively, you go in taking account of what's happened in the past. The slightly more sophisticated model is fictitious play, where instead of learning which of your actions has been most rewarded in the past, you learn which action has the other player most done in the past. In fact, it's exactly the same equation, but this is now about whether him choosing to work or to shirk is more probable. And finally, there's the influence model, where you choose the action on the basis of the expected behavior of your opponent, but also take into account the influence that your action has on the opponent, which is this extra term here, where you have the inferred probability that the opponent has about you, which is a second-order belief. In other words, if you're the employer, you would expect that after you've inspected, the employee is more likely to work, that what you do has an effect on their behavior. So these are all perfectly straightforward equations in principle, although not really in practice, which you can fit. But there's another way of looking at these 3 models. So the reward learning model is I would choose my action on the one that was most rewarded in the past. The second model is I choose my action on the basis that you will choose the action most rewarded in the past. And the third model is I choose my action on the basis that you will choose your action on the basis that I will choose the action most rewarded in the past. So you have another version of this recursion building up to more and more sophisticated models. And as I said, the more sophisticated the model, the greater the depth of recursion. So this is the result. These are the fits of the various models, and you can see that the influence, this is to the behavior of the subjects in the experiment. The influence model clearly gives a better fit than the reward learning, the fictitious play, and a complicated combination of the two, although I'm told that none of the fits are very good. This is perhaps not surprising because it assumes that people play stationarily, whereas if you actually play this game, you're constantly thinking about different strategies. But the influence model fits better, significantly better than the others, and furthermore, the greater the extent to which subjects use the influence model, the more activity you see in medial prefrontal cortex, consistent with the result I just showed you. And this is what I mentioned before. In posterior STS, left and right, you get a prediction error. That is to say, there's more activity when you don't have the expected effect on the other person's behavior. So even this quite high-level stuff where there's no movements involved at all, posterior STS still seems to be a prediction error about your estimations of the other person's intentions. But of course, this is all competitive, and what we're really interested in is collaborative behavior, because what humans are particularly good at, whatever they may say, we're not Machiavellian. What we're really good at is collaborating, and that's why we do so well, and that's why I got all these papers in Science and Nature. So what about collaborative recursion? This is the Jean-Jacques Rousseau's stag and rabbit hunt game. Again, it's a 2-player, but this time a collaborative game. You can the 2 hunters either go for stags or they go for rabbits. If you go for a rabbit, you'll get a small reward, and it doesn't matter what the other person does. But you'll get a big reward if you catch a stag, but you only catch a stag if both of you go after a stag. So if you go after a stag and the other person goes after a rabbit, you don't get anything. And this is slightly different from other economic games because there's a payoff dominant strategy. That is to say, it is indeed a good thing to go for stags, although the rabbit is the risk-dominant strategy. And Wako Yoshida at the Phil has analysed this game and has produced a mathematical model of how it should be played. And basically this involves recursive thinking, because I should only chase the stag if I believe that you will chase the stag. That is to say, I have to represent your intention. But I know that you will only chase the stag if you believe that I will chase the stag, so I have to represent your representation of my intention. And I know that you know that I will only chase the stag if I believe that you believe that I will chase the stag. In other words, I represent your representation of my representation of your representation. These are all involved in playing this game. And for the collaboration to decide to collaborate, you somehow have to solve the problem of this recursion. Basically, you need to represent your certainty about the intentions and beliefs of the other person. Are they going to collaborate? And again, they scan this, and interestingly, the activity in the medial prefrontal cortex here reflects the uncertainty of the inference about the other person's strategy. In this study, I should say, the subjects were playing against a computer which had a fixed level of recursion which changed from time to time, which makes life much easier than if you had two people playing against each other. So again, we seem to be finding this medial prefrontal cortex coming up in these interesting situations where you have to think about what other people think about you, and so on, and so on. And there's another way, and what I think is very interesting is that this recursive thinking is an example of the problem of common knowledge, which is known to philosophers and artificial intelligence people. So the problem might be A wants to meet B in the canteen at 1 o'clock. A sends B an email, but we know that emails are not reliable, so the question is, has B received the email? So B has to send a confirmatory email, but has A received the confirmation? So A sends B a confirmatory star email, but has B received the... and so on and so on. And you can prove that if there is a fault, if the probability of the email arriving is less than 1, then the logical thing is not to go to the meeting, however many confirmatory messages you get. But of course, in real life, a recursion of about 1.5 is usually sufficient. So somehow we resolve this problem. And again, this is the sort of thing that I hope the people in this audience in the future will solve, because I'm not clever enough to do it. A and B have mutual beliefs about the likelihood of emails failing to arrive, and they somehow have to estimate the probabilities, and particularly their precision about what the other person thinks they're going to do. And I'm suggesting that this problem arises whenever communication involves sharing meaning. So we have to decide that what I've said to you, you've actually understood. Because how do I know? In this case, I think it's very unlikely. So these are some speculations. Human social interactions typically require recursive representations of the mental states of self and others, and the certainties of these representations. And we don't yet know to what extent or which aspects of this are implicit or explicit. But I believe that its explicit conscious theory of mind is only involved when we need to explain to others the causes of behaviour based on our knowledge and intentions. And sharing our knowledge and intentions in this way with others enables optimal social interactions and is uniquely human. And now I shall make the mistake that all lecturers make, which is being determined to tell you about my most recent experiment because it's so exciting. Although there isn't really time. So what is explicit conscious theory of mind for? I just told you it permits the sharing experience, the generation of shared reality. Can we prove this? And I want to talk to you about the idea of the Bayesian committee. So this is an example of what happens when a single person is using information from vision and touch at the same time. And what you can show is that they combine vision and touch in a Bayesian optimal manner, so that they weight it according to the reliability of the information. So you give more weight to the more reliable signal. So in the normal case down here, I think this is right, vision is much more reliable than touch, and you base your judgment entirely on vision. But you can add noise to the vision, and up here you've added so much noise to the vision that it's not worth caring about, and you base your information entirely on touch. But there's an intermediate stage where, by combining touch and vision, you can do better than either one on their own, due to optimum Bayesian combination. And the question that we have been asking is, yes, I said all that, does the same thing happen if you have two people with the same modality? Can two people combine their information in an optimum manner and achieve better results than either one on their own? And this is the work that Bahadur has driven forward so magnificently, and he's somewhere in this audience, but I can't see him. Yes, there he is. So this is the task. We have two people doing a psychophysics experiment. This is the psychophysics experiment, which I have to remember. This is a forced choice, a two-interval forced choice oddball detection task, contrast detection task. So these are the two intervals. In each interval you see 6 patches. In one of the intervals, one of the patches is slightly more contrasting than the others, as you can see here, but you wouldn't have the ring there normally. And your task is to say which interval had the odd one out in it. So the two subjects see this, they make their individual decisions. If they disagree, then they discuss amongst themselves and come up with a group decision. So the interesting question is, how does this group decision compare to the individual decisions? This is the data from 2 examples. So the blue and the yellow lines are the psychophysical curve for the individuals. So this is their ability to say, was it in the first or the second interval? The steeper the curve, the better they are at making this distinction. And what you can see is that in both these cases, carefully chosen for this reason, the joint decision is better than either of the 2 individual decisions. So the red curve is steeper than the blue or the yellow. And this is the real result. So 2 heads are better than 1. The empirical data shows that the dyads are significantly better than the best person in each dyad working on their own. And there are various restrictions to this. They have to be roughly equal in their ability, but I don't want to go into that now. And the question is, how do subjects resolve discrepancies in their perceptions? You could just toss a coin. So all you can say is, I thought it was 1, he says, I thought it was 2. So you can't, there's nothing you can do but toss a coin. You could realize that one of them is better than the other because you've seen how successful they've been so far, so that you would choose the more, if there's a disagreement, you choose the more competent person, but in that case you can never do better than the more competent person. And the one that we think happens is you choose the response of the more confident partner on a trial-by-trial basis. In this case, because you will have, each of you will have bad trials from time to time, but it's very unlikely you'll both have a bad trial at the same time. You can eliminate the bad trials from the individuals, and you will get a better result than either person on their own. And roughly speaking, this is what's happening. So when you disagree, you not only say it was the first interval or the second interval, you also say how sure you were whether it was in the first or second interval. And there's if you're clever, you can show it. There's a simple formula giving the Bayesian optimum way of handling this kind of information. And I don't want to go into any detail here, but this is a plot of the actual data and the various models that could be applied. So along the x-axis here, we have the difference between the 2 participants. So if they're equally good, they'd be here. If one of them is half as good as the other, they'd be here. And if one of them is very, very bad compared to the other, they'd be down here. So this is the coin tossing line. This line is what you would get if you always chose the answer from the better person. And the red line here is the line you get in the confidence sharing model, that is to say, where they tell each other how confident they were in their answer. And you can see that the data fits the confidence sharing model very well, which is the dotted blue line. So I think there are at least 2 features of the paradigm that lead to the necessary for this, which could have resulted in this enhanced joint decision making. First of all, there's the communication, that is the discussion prior to the decision, but also, of course, they were given feedback about was the joint decision correct and which individual decision was correct. So which is conceivable that the feedback is the critical thing rather than the communication. So a second experiment was done where they either had communication and no feedback, so they discussed but they weren't told whether they were right or not, or they had feedback and no communication. And again, the results are very clear. With no communication but feedback, they're about as good as the best person on their own. Is that right? Yes. Mm-hmm. Whereas when they have discussion but no feedback, they get this big advantage. So the feedback doesn't seem to be necessary, but the discussion is critical. So we assume that the discussion is the key point of this task that enables you to do so well. And obviously this depends on two things. First of all, your ability to introspect on your own performance and know how confident you are. And secondly, the ability to convey this experience to each other and somehow match up your confidence scales. So metacognition and communication. So the obvious question you ask now is, what do they actually say to each other? And fortunately, our colleagues in Denmark, Christian Thulin and Riccardo Fusaroli, have been through 20 hours of video of these conversations that these people were having and have transcribed it all into text and have done textual analysis. And this is the sort of thing that people say. You know, we take yours because I saw nothing, the other because I didn't see anything either. I took a bet. It was just a bet. And they're very strange Danish phrases that don't properly translate. Another one said, I don't know. And I saw something, both in the corner and the centre or something. I think it was over on the left side. We'll ruin the scores. We must pull ourselves together, they said. Yeah. But what emerged from this detailed analysis is that people develop scales of confidence which they use to convey to each other, and each group seems to develop its own scale. And these are some examples, again translated from the Danish. So this is one group at one extreme: saw it well, saw it all right, I think I saw it, doubt that I saw anything, I didn't think I saw anything, I won't read that one out, didn't see anything, saw only a blink. So you have a nice scale here of degree of confidence. Here's another one: 100% not sure, 100% not 100% sure, 55% sure, a little sure, quite uncertain, not quite sure, unsure, too unsure, totally So these are the kind of scales that emerged, but what is, from an empirical point of view, what is interesting, they were able to measure to what extent these scales emerged and whether that predicts performance of the dyad. So this is showing you one example of such a measure. So this is what they call global linguistic convergence. So this is a ratio of the most commonly used confidence phrases against all the confidence phrases. So the more they converge on a small set of confidence phrases, the higher this ratio will be. And you see there's a highly significant relationship between this convergence on a scale for discussing confidence and their ability to have an advantage of working together above what would happen with the best person on their own. So I think this is, again, illustrates that telling each other about their confidence seems to be critical, and what people seem to be remarkably good at is coming up with such a scale in a completely flexible way in a novel situation. So, and I'm now nearly finished. So I'm now trying to put a mechanism of a kind onto these joint interactions, going back to the sort of recursive talk, which I'm now trying desperately to show how it relates to the social psychophysics experiment. So the question is, how do participants converge on common sets of phrases for describing their confidence? And I think you have to have a system something like this. You have to minimize the difference between what I mean and my estimate of what I think, or what she thinks I mean. So player one has an idea, he tells it to player two, and player two, on the basis of this, works out what player one's idea is and links it to his own idea. And if there's a discrepancy, he will then say something to indicate that there's a discrepancy. And this will go round and round and round until these discrepancies here are minimized. So the important thing, the problem with communication is I can't get inside your head. So how do I know that the idea that I've got in my head is the same as the idea that you've got in your head? The solution is that I have in my head an estimate of what I think the idea in your head is. And that's what I can use to see whether my communication is working or not. If what you say back to me suddenly reveals that you clearly haven't understood a word I've said, then I know that something is wrong, and I go around this procedure again. So if both people are trying to simultaneously minimize the discrepancy between their suggestion and what they think the other person thinks their suggestion is. And to do that, you not only have to represent what the other person's thinks your suggestion is, but you have to have some idea of precision of this estimate, I think. Because you have to decide when to stop going around this loop, when you've got sufficient information to decide that the agreement is good enough, and that will depend on this measure of precision. If you really have a very poor idea of what the other person thinks you think, you probably start doing something else instead. So these two components of the process are necessary, and I think that's what's relating to metacognition. We not only have to have the representation of the signal, but we have to have a representation of the reliability of the signal. And I should add, which I haven't put in here, is that recent studies of explicitly looking at our ability to do metacognition, though not in relation to this kind of task, consistently suggests that very anterior prefrontal cortex is involved, just as we have already seen medial prefrontal cortex is involved in all these mentalizing tasks. So finally, my last slide, this is a plea to you all, particularly these people sitting back here, that we need to model behavior not at the level of the dyad, not the individual. So we want to do this whole thing. Most of the time we just look at this. We want to do all that. And likewise, we need to model the brain activity at the level of the dyad and not of the individual. So that's what I hope will happen in the next few years, so that next time I come here, I can talk about other people's work and how they have solved this particular problem. So this is all very speculative, but I think we're actually beginning to see mechanisms that could be used to explain how we do theory of mind, which is probably the most interesting thing that we do. So thank you very much. These are the people who financed me. My intellectual gratitude is to the people in Aarhus, the Interacting Minds group, and the social club at UCL. And you heard about this already. Yeah.